This is Precalculus, Chapter 9, Lesson 3. Ladies and gentlemen, we're on page 593. This lesson is on other identities. I want to connect them to what you've already learned. Without looking at your identity sheet, can anyone tell me what the sum formula is, or the sum identity is for the sine? The sine of the sum of two angles is, Corinne?
It's sine of x times the cosine of y plus the sine of y times the cosine of x.
Right. Sine, first one, cosine, second one, plus cosine, first one, sine, second one. What if they're the same angle? What if we're adding the same angle? Then what would that look like? It'd look like the sine x cosine x plus cosine x sine x. Are those like terms?
Yes.
How many of them do we have?
2.
Look at your double angle formulas. You'll see that the sine of any double angle is this. It's derived from the sum. All right, what about the cosine? Cosine's the boss, remember? So who can tell me the cosine sum formula without looking? Cosine x, cosine y, minus sine, sine x, sine y. What if they're the same? Then it's cosine x minus sine x, sine x. What's the cosine x times cosine x? Cosine squared x minus sine squared x. That's your double angle identity for the cosine. We get other ones by substituting what we know. What do we know for the cosine? What could we substitute in for the cosine squared? 1 minus sine squared x. So that would be 1 minus sine squared x minus sine squared x. We have two like terms. 1 minus 2 of them, sine squared x. So that's another one for the cosine. Depends on what we want to substitute in. What can I substitute in for the sine squared x? 1 minus cosine squared x. So if I do that, substituting in 1 minus cosine squared x, distributing the negative, cosine squared x minus 1 plus cosine squared x. We have two like terms. So it's 2 cosine squared x minus 1. Minus 1. All right, so we have three options for cosine double angle. Depends on what we want to do. If we want to go all to sine, this is where I'd go. If we want to go all to cosine, this is where I would go. All right, what's the tan? Tan of double angle. Plus, let's just think of plus. Plus is plus minus. What's plus in the numerator? The tan of the first one plus the tan of the second one. Over 1 minus them multiplied. All right? So if they're the same, then we have tan x plus tan x over 1 minus tan x times tan x, or 2 tan x over 1 minus tan squared x. And that's your double angle. That's the tan of 2x. That's your double angle formula for the tangent. All derived, everybody agree? All derived from the sum and difference. That's why I make it a big deal to memorize the sum and the difference, so that you automatically know your double angle identities. All right, we've had double angles, actually. We have had things like the sine of 2x equals 1, and we substituted 2x, we substituted u for 2x, right? And then we plugged 2u back in, 2x back in, and then divided every term by 2. All right, so this is sort of familiar territory. So let's look at example 1. Example 1. Let me go ahead and say this before I forget it. On your test, the only identities I will give you are the identities from this lesson that are labeled 9.3. You will get a sheet of paper, and it will just have 9.3 identities on it. You will not get anything from 9.1 or 9.2. All right? All right, so example 1 says, use double angle identities. And it tells us where this angle is. And so what quadrant is the angle in? Quadrant 3. So we know it's there. And it tells us the cosine of x. So this would be, all here would be x. Negative 8 over 17. Well, we use the Pythagorean theorem to solve for the other side, and it's 15. 8, 15, 17. And it wants us to find the sine of 2x and the cosine 2x. Well, if I were asked this, I would just say I'm just using sum and difference. That's all I would do. I wouldn't do my double angles. I would just do sum and difference, because I know that 2 times x is the same thing as x plus x. All right, so let's do our sum and difference. We're going to do enough double angles, but I do want you to know that you can always just use the sum. All right, the sum is sine cosine plus cosine sine, right? So that would be sine x cosine x plus cosine x sine x. All right. So what is the sine of x? It already gave us the cosine, right? Negative 8/17, negative 8/17. What's the sine?
15.
And it's also negative because it's in the third quadrant. All right, what's 15 times 8? Both will be positive. And 17 times 7? 15 times 8, go. Yes. 120. And 17 times 17.
289.
289. So that's 240 over 289. All right. So the sign is positive, right? The sign of the double angle is positive. It wants us to show what's 5 pi over 2 to 3 pi. What quadrant is that? 5 pi over 2. It wants us to show that the double angle is between 5 pi over 2 and 3 pi. Yes. Because they're going 2 pi to 3 pi. So this is going to be quadrant 2. Does that work for the sine of 2x? Yes, because it's positive in the second quadrant. The sign is positive in the second quadrant. All right. Now let's do cosine. Cosine's the boss. He goes first. So it's the cosine x times the cosine x minus sine x sine x. Cosine is negative 8/17, so we're going to square it, minus sine x, negative 15/17 square. Somebody square the first term, somebody square the second term. I already know 17 times 17 is 289, if that in fact was right. I believe, Jake. 8 squared is? Yes, sir.
If the radian measure ends on a line, how do you know which quadrant it's in?
Okay, if the radian measure what?
Ends on one of the lines. How do you know which quadrant?
Well, it's actually on the axis, isn't it?
Yeah.
So pi to 3/2 pi is here, but notice there's no equality. Quadrant 2 has no equality when we're looking at that. So it's on the axis. Got it? What's 8 squared? 64. 15 squared. 225? Is it 225? What's 64 minus 225? I know it's negative 161. Cosine of the double angle is negative. It is negative in the second quadrant. The cosine's negative in the second quadrant. So we have actually confirmed that. Make sense? Yes.
What if it was in the second quadrant? Would we just say not a solution, or?
Well, they have to both be in the same quadrant because we're just doubling the angle. When you double the angle, you're just rotating it around.
So if it's not, then we did something wrong?
Yes, correct. If you would have gotten a positive here and a positive here and your original, well, then it would have been in quadrant 1. A positive and a positive, I would have said would have been in quadrant 1.
So it would be wrong because we're looking for quadrant 2.
Well, then we would say it's not in quadrant 2. It's in fact quadrant 1. When you double an angle, do we know what the angle is? We don't know what the angle is. Can we find out what the angle is? How do we find out what the angle is? Inverse. Okay, let's find out what that is. And if we double it, couldn't we figure out what quadrant it was in? All right, somebody calculate that angle. What are you using? Which trig ratio? Sine? Inverse sine in radians, right?
I got 1.08.
You got 1.08. All right, you got to add pi to it. So that's what? 4.22. We'll say 4.22. Times 2, that's 8.44. Right, all the way around is what? 6.27. Let's add a half a pi, because that would be a half a pi. Let's just do 3.14 divided by 2. So that's 1.57. Gets me to 8 point, is that right? No,
No.
7.84. All right, so quadrant 1 is between 6.27 and 7.84, right? Quadrant 2 would be between this and another half a pi. That's 11, that's 14, that's 9. It is in quadrant 2.
Why did we multiply by 2? Oh, because it's 2x.
Yes, yes. All right. Now, when are we really going to use double angles? Look at example 2. State the rule of the function f of x equals a sine of 3x in terms of sine of x and constants. I'm going to have to pick up my pace a little bit. All right, so if I have f of x equals a sine of 3x, we could say 2x equals y, so that 3x equals x plus y. Do you agree? Or we can leave it x plus 2x. Yes. Yes. Wait, right here. Well, you don't have to blow your nose. You know what I'm saying. You have to go search. All right. So let's make it sine of x plus 2x. That's my sum, right? Do you agree we have the sum? All right. So what does that equal? Sine of, no, we're going to do the sum formula. Sine of x, cosine 2x,
Plus
cosine x, sine 2x. Now we have two double angle identities. So for 2x, we're going to use cosine squared minus sine squared. For sine of 2x, we're going to use 2 sine x cosine x. Look at your identity sheet. All right, we're just going to substitute. For this one, we're substituting cosine squared x minus sine squared x. Everybody with me? With me so far? Plus, then we're going to substitute 2 times sine x cosine x for that. All right, cosine x to sine x cosine x. All we did was substitution, right? We want everything in the terms of sine x. That's the goal, to get everything to the sine. All right, let's distribute. All I'm doing is distributing. So we'll distribute the sine. So we have sine x cosine squared x minus sine cubed x. You with me so far? We'll distribute, it's just one term, plus 2 sine x cosine squared x.
Where did you get 2 sine x cosine?
For sine 2x.
But where did the cosine come
Which
In
cosine?
the parentheses. it's-
Here?
Yeah.
Look at your identity sheet for sine 2x. You see your identity sheet? Sine 2x is 2 times sine x cosine x. Which is actually what we wrote on the board to begin with, right? All right, do we have like terms? It's on the bottom left-hand corner, bottom left-hand first column. We have like terms. Everybody see like terms? So there's 3 of them. 3 sine x cosine squared x minus the sine cubed x. We want everything in terms of sine. Yes.
Do 1 minus sine squared.
For cosine x, I'm going to make it sine. That's right, 1 minus sine squared x. So now I'm going to substitute right here. 3 sine x times 1 minus sine squared x minus sine cubed x. Everybody with me so far? We just distribute. So we have 3 sine x minus 3 sine cubed x minus sine cubed x. Do I have like terms? How many do I have? I have 4. So it's 3 sine x minus 4 sine cubed x. Is everything in terms of constants and the sine?
Yes.
Done. Got it? Yes?
So our goal was to get everything in sine.
That was the instructions for example 2. Yes. Express the original rule in terms of powers of sine and constants. All right. Let's look at the next example. Example 3. Now we're going to prove that something on the left-hand side equals something on the right-hand side. 1 minus the cosine 2x over the sine 2x equals tan x. Okay, we're obviously going to work on the left-hand side. Everybody agrees? What does the tan equal? What over what?
Sine over cosine.
Sine over cosine. So the goal would be to put sine in the numerator and the cosine in the denominator. You agree? Mm-hmm. Okay. So when I look at my cosine double angles, I'm going to choose one that only has the sine in it. Do you see you have 3 options? Mm-hmm. So if I want the sine in the numerator, which one would you choose? 1 minus 2 sine squared. So it's 1 minus 2 sine squared. Okay, we'll eventually work on the denominator. Let's see what we have in the numerator. All right. Well, 1 minus 1 is 0. Well, we have to distribute that. That's 2 sine squared x over sine 2x. I only need 1 sine in the numerator. So I know whenever I use in the denominator, I want to at least pull out 1 sine. Well, we only have 1 option for sine 2x, right? Mm-hmm. What is it? 2 times sine times cosine. So I substitute that in. 2 times sine x cosine x. Cancel. Yes. I knew I wanted to get rid of a sine. So I end up with the sine x over the cosine x, which is in fact the tangent. Make sense? Okay, so you look at where you want to go, and that, for the cosine particularly, dictates what you want to substitute in. Okay, so maybe, possibly, you'll begin a proof, and it won't get you anywhere. We'll go back and try another identity, right? If you hadn't thought of what you needed to use at first. All right, look at example 4. We're going to use the power reducing formulas. Let me see your formula sheet. I put the radicals on your half so that you see the power. Let me just, let's look at this. We have power reducing. From the power reducing, we get the half angle. All right, so let's just look at the sign. The sine squared x. That's when we want to reduce an exponent. That's when we're going to use the power reducing. It does equal 1 minus the cosine of 2x over 2. In your sheet, I put the radical. There's no radical in power reducing. But we do take the square root to get to the half angle. All that we have to do to get from power reducing to the half angle is this goes under the square root, the 2 goes away. So to get to the half angle, it's plus or minus the square root of 1 minus the cosine of x over 2. All right, so there's no radicals in your power reducings. Does that make sense? I put them there to show you get from power reducing to your half angles by taking the square root. And this is half angles. The reason we would use half angles is, suppose I have an angle. Suppose I have an angle. And it is not on the unit circle, but half of its angle is. But half of its angle is. So how do that's when I'm going to use the half angle. Dividing by 2 is the same thing as multiplying by 1/2. Or taking half, dividing by half. That's right, when we divide it into half. When we divide it into half, that's the same thing as multiplying by 2. So you get an angle that is on there. All right, so here's how you know. You always look at the denominator. 5 pi over 8 is not on the unit circle, but half of its angle is 5 pi over 4 is half of its angle. You always look at the denominator and take half of it.
Isn't that double the angle? That sounds funny, but that's a little confusing.
Double 5/4. No, you multiply numerator and denominator. Half of this angle is 5/4. So 5/4 divided by 2 is 5/8.
So isn't that double it? Like it'd be
Okay, let's do 5/4. 5 pi over 4 divided by 2. We would multiply by 1/2 over 1/2. It's 5 pi over 8. We get the original angle. So the original angle compared to the half angle, I just want you to see that the denominator is always twice. So when you have an original angle and you say, like, okay, just things are coming to me. What would be its half angle? Pi over 6. Because it equals pi over 6 divided by 2. Yes.
But how would we use that?
Okay.
Why is that easier than just using the regular?
Well, this, we have to use our calculators. This, we get an exact value.
And then the exact value would just divide it by 2.
No, we're going to use the formula. We'll then use the formula. The formulas are in the textbook. All right. So let's start with the power reducing, which are under your first column. All right. So we're going to cover both power reducing and half angles. All right. So we want to use power reducing.
So you don't use the radical if you're just doing power reducing?
Correct. And they are they're in your textbook on page 595 in the box. Well, that's the sine and the cosine. All right, so we're going to reduce sine to the 4th power in terms of constants and first power cosines. So we want to go to first power cosines. All right, so that's the same thing as the sine squared x times the sine squared x. Do you agree? Mm-hmm. What does the sine squared x equal? It's an identity. Look at your page. What? 1 minus the cosine 2x over 2. 1 minus the cosine 2x over 2. See it? Now we're just going to FOIL it. The denominator is 4. That's easy. All right, so we do 1 minus cosine 2x minus cosine 2x. Negative times a negative is? Positive. And we end up with positive cosine squared 2x. Got it? It said we wanted everything first power cosine. Here's our only issue. It's not in first power cosine. We can combine these two. They're like. All right, so let's do that before we do something with this. It's 1 minus 2 cosine 2x plus cosine squared 2x all over 4. So for this one, I'm going to use the power reducing for the cosine. Notice, notice how similar the cosine and the sine are. The sine is 1 minus cosine 2x over 2. What's the cosine? 1 plus cosine 2x over 2. All right, everybody look. What is my value for x when I plug it into the 2 times the x? This is the value for my x. So it's going to be 4. That's right. right, so it's 1 minus 2 cosine 2x plus. Now I'm gonna substitute in the power reducing for cosine. It's 1 plus cosine 2 times whatever my angle is, which is 2x, all over 2, all over 4. All right, so let's simplify that a little bit. 1 minus 2 cosine 2x plus, do I want to go to 1/2? I'm going to go to 1/2 plus cosine 4x over 2 all over 4. Well, what do you think I want to do now? It's algebra. What would you do?
Multiply bring the denominator to the top.
You can. And so how would I do that?
Multiply by 1/4 over 1/4.
1/4 over 1/4 every term. Every term by 1/4. So I end up with 1/4 minus 2/4, which is 1/2. Cosine 2x, yes. Plus 1/8 plus 1/8 cosine 4x. You agree? I mean, I just pulled the 1/8 out in front. All right, let's combine the 1/8 and the 1/4. Common denominator. That's 2/8 plus 1/8. That's 3/8 minus 1/2 cosine 2x plus 1/8 cosine 4x.
And is that your answer?
Is everything in first power cosine? Final answer. Make sense? Got it? All right, let's work the half angles. With the half angles, we do have the radicals. We use the half angles because we want to find an exact value. Look at example 5. Look at the instructions. Find an exact. When you hear that word, what should you automatically think? I've got to use the unit circle. I have to. All right. So we have cosine 5 pi over 8. And we have the sine pi over 12. Cosine is plus, sine is minus. That's how I remember it. Cosine plus, sine minus. They're really the same formula. All right, first we have to decide what quadrant is this in? 5 pi over 8. It's in quadrant 2. All right, so I really want to use half angles. This also has to be in quadrant 2. Because this is the same thing as this. Notice in your formulas, it's plus and minus. It's plus and minus, isn't it? It's not both plus and minus. The plus or the minus is dictated by what quadrant the original angle is in. So in quadrant 2, what's the cosine?
Negative.
All right, so my answer is going to be negative. Oops. Got it? So I automatically know my answer is going to be negative. So here's my x value. My x is the numerator because it's the cosine of x over 2. So it's going to be the negative of 1 plus the cosine 5 pi over 4 divided by 2. What's the cosine of 5 pi over 4? What quadrant is this in?
Second.
It's in the third, because it's bigger than pi. So it is negative square root 2, 1 plus negative square root of 2 over 2 over 2.
Why did you say it was in the second? Did you just mean the whole?
This sign out here, the sign outside your radical is dictated by the quadrant of the original.
Okay, so 5
Radian.
4.
So 5 pi over 4 is in the third quadrant. It is negative. Whatever we end up with, it's going to be negative.
So I think why isn't it in the second quadrant? It's supposed to be the same angle.
It's not. It's half of that angle. But with the formula, we use that angle.
So
The formula is
and will it go back to the second quadrant because the 2 that's
We're-
in
it will. It's gonna be negative.
Okay.
Okay. So let's work under the radical. We know we're gonna have. Let's make this 2 over 2. Actually, let's separate numerator and denominator. We can do that. Square root of 2 over 2 minus square root of 2 over 2 all over square root of 2. Right, we can do that. So this equals the negative square root 2 minus square root of 2 over 2 all over square root of 2. How could I rationalize that?
Multiply by the square root of 2.
Okay, is that the same thing? I'm going to use all this board, huh? I'm going to write this over here. That's the same thing as the square root of 2 minus the square root of 2 over the square root of 2 over
Yes.
square root of 2,
Yeah.
right? How do I rationalize that denominator?
You just
Multiply by the
square
square root.
I really want to multiply by 1 over the square root of 2. Over 1 over the square root of 2. Because I want to eliminate that denominator. I don't want to rationalize it. 1 over the square root of 2. 1 over the square root of 2. Right? I want to eliminate it because I have a complex fraction here. So that ends up being, oh, I lost my negative. Negative square root of 2 minus square root of 2 all over 2. That's got to be the final answer. Final answer. A rational denominator is what you're looking for. Got it? Just a little hard algebra. All right. Now let's do this one. What is pi over 6 a half angle of? Pi over 12. I gave the answer. Pi over 6, right? So the sine of pi over 12. Well, what quadrant is it in?
Pi over 6 is in the first.
This one, pi over 12.
Also the first quadrant.
Yes, both are in the first quadrant, but you're looking at the original angle to decide whether or not my radical is plus or minus. All right, so I'm going to do the sine of pi over 6 over 2. And I know I want it to be plus cosine is positive, sine is negative, but it's still cosine. Well, now we're looking at pi over 6. Pi over 6. All right? What's the cosine of pi over 6? Square root of 3 over 2. All right, so I'm going to make numerator, denominator. That's 1 minus square root of 3 over 2. Common denominator, 2 over 2, right? I remember it's going to be positive. So that's the square root of 2 minus square root of 3 over 2, all over square root of 2. Going to follow the same procedure, split the numerator, all under a radical. We write down here, square root of 2 minus square root of 3 over square root of 2 over square root of 2. I have a complex fraction. Let's eliminate the denominator by multiplying by 1 over square root of 2 over 1 over square root of 2. And I end up with square root. It's easier the second go around, isn't it? Because you anticipated what you needed to do. And that one would be positive. Thus, you anticipated it, right? Okay. Let's do another half angle. Example 6. It's a little different. It's the tan. We have options for the tan. There are actually 3 or 2 options. Well, they're on the top of your book. I have written them in your on your sheet. I'll make y'all a new copy because I don't have radicals on mine when we take a quick break. All right. But we want to use half angles. The tan of x is 3 halves. X is in what quadrant? It tells us between pi and 3 pi over 2. It's in the third quadrant. It's opposite over, it's opposite over adjacent. Both are negative. What is the hypotenuse? 9 and 4 square root of 13. You have to square them. A squared plus B squared equals C squared. All right. So now this is X. We don't know what X is, but we're going to solve for the tan of X over 2. Yes. All right, so we could either use 1 minus cosine X over sine or the sine over 1 plus cosine X. I like a single term in the denominator as opposed to something adding. So I'm going to use the first, 1 minus cosine X over sine. It's easier than having a binomial in the denominator. I don't know. Just seems simpler. You could do it either way. You would get the same answer. All right. So it's 1 minus, what is the cosine of that angle? Negative 2 over square root of 13. And the sine X is? Negative 3 over square root of 13. I'm going to make a common denominator in the numerator. Square root of 13 over square root of 13. Because then I'm just going to eliminate that denominator. This ends up plus, that ends up minus. So our whole term ends up being a negative. All right. Square root of 13 plus 2. over square root of 13 over 3 over square root of 13. Let's eliminate our denominators, and it's negative square root of 13 plus 2 over 3. Final answer. What quadrant is it in? Half of that angle is in quadrant, what do you think? Has to be quadrant 2 because the tan is negative. Half the angle is located in quadrant 2. Is that logical? It's logical, right? Had to rotate back to this quadrant. All right, last one. Sum and product to sum to product. All right, these are on your sheet. I actually want to work 2 problems from your homework. Which ones did I work? I don't work 14 and 22. 14 and 22. All right, let me go to 14. I'm going to write them both on the board. That's 14. I'm going to write 22 over here. All right. These terms are multiplied. When you have terms multiplied, you're typically going product to sum. Make sense? When the terms are multiplied, you're typically going product to sum. So in fact, all of 13 through 18 says to write the expression as a sum or difference because all of them are multiplied. When they're multiplied, you're going product to sum. These are added. So we're going sum to product. All right, so when they're added, you're typically going sum to product. Make sense? All right, you have all the identities on your sheet. The product, it's the sign times the sign. That tells me which one to use. It's the very first one. Right? The very first one. That's all I'm going to do. I'm going to substitute it in. It's 1/2 times cosine 5x minus 7x minus cosine, and I'm adding them. 5x plus 7x.
Which one are you looking?
The very first one. Product to sum.
Is that any different from the power reducing? Or like why would
It
you
is.
Why would you use the power reducing one? I think it's what Brent asked.
That's when you have an exponent. There's no exponents.
So these are more, or are you just gonna-
What's an exponent?
Well, it's when it's raised to a power.
Right, that would be power reducing.
But these signs are multiplied by each other.
Yes,
So,
but they're different angles. Not like terms. Can't combine them. Right, it's not like you add the angles or anything, right? They have to remain separate. 5 times an angle is probably not in the same quadrant as 7 times an angle. Okay? All right, so let's just do the algebra. All right, what about this term? Can I do something with this term? What do you remember? Look at this. Okay, anyway. Obviously. Okay. Anyway, yeah.
Can you do a double angle example?
Well, Is that true?
Yes.
Yes, it is true. All right, so I'm gonna distribute that and I'm gonna change that to positive. Final 1/2 Paul. 1/2 goes here as well. Final answer. This is it.
Why is that? Is that always?
Got it? Yep.
What are we solving for?
We are writing this expression as the sum of angles. That's what it said. Write the expression as the sum or difference of angles. That's all you're doing. You're writing terms that are multiplied as sums. That's it. Yes.
So why do you have to remove the negative? Is it because it's not fully reduced? If you don't get rid of the negative?
Yes. You're going to see that here as well. All right. Cosine. Now we are adding. And we want to express the sum of these angles as a product. So we have cosine minus cosine. That's the very last one. All right, so it's minus 2 times the sine of the angles added divided by 2. You see that? Times the sine of the angles subtracted divided by 2. Just plugged in. Just saw, right? I'm just plugging in. All right, so we'll simplify. That's negative 2 times the sine of 12x over 2 times the sine of negative 2x over 2. I can simplify that. All right, I don't really like this negative in here. Can you look on your trig identities? What can I change for the sign of negative x? Negative sine x. All right, so the sine of negative x is the same thing as negative, it's times the sine of the positive angle. All right, so it's negative 2 sine 6x. I'll just put a negative 1 out here so we see that. Times the sine of positive x. A negative times a negative is a positive. So final answer is 2 sine 6x sine x. And that's our product.
Where'd the negative 1 come from?